correctly.
We're good? Alright, guys, could you please do the attendance form?
I've already done that. I'm eager to be learning. Okay. I'm at the 1B. How do you?
So true.
On the screen. On the screen. Yeah.
Okay, right, we'll just get started. Alright, I'll be going over vector spaces and linear transformations, and then Jiang over there will be going over eigenvalues and probability. Okay. Alright, so we'll begin with vector spaces. So first of all, our definition of a subspace. So essentially what we want to check every single time we do a question like this is the zero vector, vector addition, and close on the scalar multiplication. Yeah, pretty straightforward. So do you guys have a go at the first question? I'll give you guys like 1 minute. Okay, I'll start going over it. But essentially what we do to prove that if it's either a subspace or if it's not, we just check the three conditions. So if it contains a zero vector, close on the vector addition, and then scalar multiplication. Okay, so first of all, if we sub in the zero vector, we just get 0 plus 2, 0 plus 2, 0 is equal to 0, which is greater than or equal to 0, right? So therefore, like, it does contain the zero vector. Next thing we check is we can take a look at scalar multiplication actually, and then what we actually realize is that if we sub in lambda equals to -1, and then take out vector as something like 1, 1, 1, well then you're gonna get -1. I mean, like, your lambda is just -1, -1, -1, and then you get -1 plus 2 brackets -1 equals to -3, which is not greater than or equal to 0. So like if one of the condition fails, then obviously S is not a subspace. Yeah. Any questions?
How do we know V is in S?
Because 1, 1, 1, it's a three-dimensional vector. Yeah. It's an R cubed, yeah. And yeah, these are the solutions. Yeah, nothing too interesting. Okay. I'll give you guys 1 minute to take a look at this question. So this is clearly just like one of the features of proving a subspace.
I have a question.
Yeah.
What's a subspace?
It's just a set of vectors that follow a certain condition, right? And like it has to obey like the three properties, that being there contains a zero vector, close under vector addition, and close under scalar multiplication.
That makes so much sense now.
Okay, so essentially what we can do is we can just define a general vector, let it be like x, y, z, and then we say that this is in S, and then we also let and lambda be a real number. So lambda v would equal to lambda x, lambda y, and lambda z. We can sub it in, see what we get. So on the left-hand side, we get lambda x all squared minus lambda y all squared, which we can factorize out lambda squared. Yeah. And then factorize it, we get x squared. Oh, sorry. Yeah, x squared minus y squared, and this is equal to lambda z squared, which is lambda z all squared, and that's equal to x3 squared. So, which equals to the left. So basically it holds on the scalar multiplication. Yeah. Just to note that this doesn't prove that it's a subspace, right? It's only one of the three features. Okay. Once again, yeah, same thing. Okay, moving on, next thing we have is something called spans. Span is just a set of vectors that can be represented as a linear combination. Once again, I think this is still pretty foundational. But any questions with spans? No? Okay. All right. Yeah, could you guys have a go at this question? Can anyone give me the method straight away?
You make the matrix,
Yeah,
then you can reduce it,
yeah.
and if you have only columns, then it's a standard set. Or like they using span.
Pardon?
If you reduce it and it's like all of the columns are leading,
Yeah.
then they using span. Is that right?
But why though? I mean, it's
You
more so
get
just
all-
that
yeah,
like
you
if you get a
solution.
solution, right?
Yeah, so you get a solution.
So just that like if you have the
So like every variable is like fixed with something like.
You get a distinct solution for each, like.
no, basically you just have to say that the system is consistent, right? And that's
Yeah.
because like the leading columns. It's like the keyword here is just like saying the word consistent. But yeah. I mean, I can quickly write the matrix, but essentially what we get is 1 minus 1, 2, 1, 2, 5, 2 minus 3, 3, and then minus 1, 6, 3. And then if you do row reduce it, you'll get 1, 0, 0, 1, 3, 0, 2 minus 1, 0, minus 1, 5, 7. Yeah, in this case, the system is consistent, right? And then we can find a solution. So in this case, take a look. We have a free variable, so we can let like lambda 3 equals to 1. Well, in that case, 3 lambda 2 minus 1 equals to 5. And then this means that lambda means lambda 2 equals to 2. And then we have lambda 1 plus 2 plus 2 equals to minus 1, so therefore lambda 1 equals to minus 5. So therefore we can say that minus 5v1 plus 2v2 plus v3 equals to the vector b. Yeah, so I guess part A is just that like b is in fact in the span v1, v2, v3. And for part B, anyone have any ideas? So we want to prove that it's just a spanning set, like the entirety of R.
So the three of them have to be linearly independent, right?
Yeah. Okay, I'll just go through it. So basically, once again, it's the same thing, except this time you'll realize that it has to basically everything's the span of v1, v2, v3 has to span the entirety. So every single three-dimensional vector. So essentially what we can do is we can just like say that lambda v1 plus lambda v2 plus lambda v3. Wait, sorry. Lambda 1 v1 plus lambda 2 v2 plus lambda 3 v3. And then this is equal to our vector xyz because it's just any general three-dimensional vector. Doing what we did before, we can write the matrix again. Except this time we replace the right side with xyz. Similarly, we row reduce it, right? So we get and on the right side you should get x plus y minus 3x minus y plus c. Okay. Up until this point, we can look at the last row and we realize that if we want the system to be consistent, like for part A, right, so that there is a solution, we need minus 3x minus y plus c equals to 0. Because anything else would lead to inconsistency. And if we have this, we just rewrite it as z equals to 3x plus y. Essentially, we're saying that for x, y, z, if all three of these values hold for like any vector, then this condition is true. But we could also
Yeah, once you feel.
Yeah.
Once you feel.
Like,
But if we find any counterexample to z equals to 3x plus y for any random 3D vector, then we know that it's not going to span the entirety of our cubes. In this case, it's obvious that it's not everything, right? If we find a counterexample, we can say that maybe v equals to 0, 0, 1. Clearly 1 equals to 3, 0 plus 0 equals to 0. 1 is not equal to this, right? So in this case, we can say that therefore v1, v2, v3 does not span our cubes. Any questions with this? Yeah, so same as part A, except we generalize. Okay. Yeah. Okay, moving on. Next thing we're going to talk about is linear independence. So that's the definition. I guess the informal definition is just like an alternate way of saying it. I don't think you'll ever have to define it anywhere. So yeah. So S is linearly independent if the only solution to the equation is when all your scalars are equal to 0. Okay. Any questions with definition? No? All right. Yeah. I think yeah. So as you can read, basically these are like the two other ways to prove linear independence / dependence. No questions? Yeah. Okay. I've got this question. I'll give you guys like 2 minutes. Okay, I'm gonna quickly go through this. So for S1 is really just the definition, but essentially we only have one vector in S1, and if we have one vector in S1, it is linearly independent if and only if that vector is non-zero. And we know that U and V are linearly independent. If U and V are linearly independent, that means U is not equal to V, which then means that U minus V is not equal to 0. Okay.
It's not.
Yeah, so we know that U and V are linearly independent. So therefore U is not equal to V. So therefore U minus V is not equal to 0. And so this means that S1 is linearly independent by the definition which I just said. Yeah. Any questions on S1? kind of just like using the definition. Okay, for S2, we kind of also use the definition. So essentially what we have is lambda1 u minus v plus lambda2 v minus w, and then we let this equal to 0. If we expand it, then we have lambda1 u plus lambda2 minus lambda1 v minus lambda3 w, and this gives us also 0. And we already know that u, v, and w are linearly independent, and okay, if u, v, w are all linearly independent, therefore our coefficients of those are also linearly independent. Not linearly, like just equal to 0. So lambda1 equals 0, lambda2 minus lambda1 equals to 0, and lambda3 equals to 0. So therefore lambda2 is also equal to 0. So all three coefficients are 0, so therefore S2 is linearly independent. Okay. Last one is S3. S3, if we just take a look at the addition of all three of those vectors, u minus v plus v minus w plus w minus u. If you take a look, this actually just gives us the 0 vector. However, the coefficients of every single one of these vectors are 1, and that is non-zero. Hence, it means that S3 is linearly dependent. Because the coefficients can only be 0, like all of the coefficients, for it to be linearly independent. Any questions? Speak up. Okay, all right. Yeah. Okay, moving on, we'll talk about basis and dimension. Okay, a basis is, you can see the definition, it's just linearly independent and a spanning set for V. The dimension is the number of vectors in a basis. Okay. Any questions on the definition? Okay. Yeah. All right. I'll give you guys 2 minutes to have a go at this question. Okay, I'm gonna go through this question. Okay, there's no space. Yeah, so first of all, if we want to show that B1, B2, B3 is a basis for this field, then we can consider the matrix one, just putting the three vectors together. And if we row reduce this, we should get the second matrix there. And then if you take a look, all three of them are leading columns, and so it basically tells us that the three columns are linearly independent. And this field is F cubed, which means that there are three linearly independent vectors in this field by definition. And we in our columns we have three linearly independent vectors, not more, not less. Therefore, we can just say that B1, B2, B3 is a basis. So yeah, three linearly independent vectors. Okay, and for part B, if we look at the table, what we realize is that under addition, when you add each vector by itself, actually, no matter what, just results in 0. So if you take note that B1 plus B1 would equal to 0. So therefore, we can say B1 plus brackets B1 plus B2. So essentially, like the first and second vectors added together, this would just give us 0 plus B2, which just gives us B2. And we have B1, the addition of these two gives us B2, and then we also have B3. So therefore, it is a spanning set because B1, B2, B3 is a basis. Any questions with this part?
Why is that one not a basis?
Well, first of all, that was the next part, right? I haven't explained that yet. But like, it's not a basis because first of all, we're only meant to have three linearly independent vectors in F cubed by definition, and in this case, we look at this set and it actually has four vectors. Therefore, one of them must be linearly dependent. Additionally, we can also take a look at what happens if you just like add it up, right? If you just do B1 plus B1 plus B2 plus B2, B3 plus B3. There's two of each, and whenever you have two of each in this field, you get 0. So everything's just 0. And clearly the coefficients for each are not 0, they're 1, right? So therefore, it's not a basis. Any questions? Yeah. Okay. Okay, coordinate vectors. This is 1 to 4 and only. It's really just what we did before, except it's just solving for like the coefficients again and then putting it into a vector. Yeah. I'll give you guys 1 minute to have a go at this question. Okay, similar method, right? Once again, we just have our matrix 1, 2, 5, 0, minus 1, 3, and then our V is 10, 3, 2, 1. Similarly, we just row reduce it. You should get 1, 1, 1, 0, 0, 0, and then 4, 9, 28, 10, 17, 56. Same method as before. We just use back substitution, and we'll realize that lambda 3 gives us 2. So lambda 2 plus 9 times 2 gives us 17. So therefore lambda 2 is minus 1. And then lambda 1 minus 1 plus 4. 4 times 2 gives us 10. So therefore lambda 1 is equal to 3. And so therefore our coordinate vector is just 3 minus 1, 2. Any questions? We're just finding the coefficients and putting it into a vector. Yeah. Okay. Alright. Okay, now next topic, linear transformations. So here is the definition of a linear transformation. Same thing as a linear map. And so essentially, once again, we have to preserve vector addition and preserve scalar multiplication. The note says that you say preserve and not closed, but it's basically just use the word preserve because you're dealing with functions, not sets of vectors. Yeah. Yeah, but that's the definition. And then this is to check if something is linear or not. All right. Could you guys have a go at this question? Okay. I'll go through the question. So essentially, if you look at the definition above, we've basically just kind of used this definition here. And so if we sub it in, we can use let's say t of AP plus BQ x, where let's say PQ be polynomials, and then AB are constants. Okay, so writing this out, we should get x squared plus 1, AP plus BQ dash x minus 2x ax plus BQ x. I'm just replacing P with AP plus BQ here, and then you should get expanding it, x plus 1, AP dash x plus BQ dash x minus 2x, AP of x plus BQ of x And then if we expand out,
You wrote X and put it pretty much something.
That's AX.
wait, what?
You wrote AX plus BQ, so AP plus BQ.
Oh shit. Okay, AP plus BQ. Thank you for noting that out. Yeah, continuing on, you have x squared plus 1 p dash of x minus 2x p of x, and then plus b. Okay, I actually don't have space for it. X squared plus 1 q dash of x minus 2x q of x. Okay. Ultimately, if you just like look at this, you'll realize that it's just a t of p of x plus b t of q of x. And that follows our definition above. So it will get us this part. Okay, so therefore, because these are equal for our map, therefore we can say that this is true. Yes. Okay. Can you guys have a go at this question?
Finally makes us do geometry.
So true. Okay. Here the question says that it just reflects any vector about the line y equals root 3x, and it would be helpful for us to know what that angle is that it makes with the x-axis, and we can just figure it out. So if we define this theta here, which is the angle that y equals square root 3x has to the positive x-axis, theta is just tan inverse of root 3, and that gives us pi on 3. So theta is pi on 3. So our first vector is 1, 0, so like look something like this. But essentially we're just reflecting it about this line here, right? So it looks somewhere here. This angle is pi on 3, which means that our other angle here is also pi on 3 because it's symmetric. So therefore we know that it's going to be some vector here that's also pi on 3 more. So have a total angle of 2 pi on 3. Note that the length of this vector doesn't change because we're purely reflecting it. So we can just say that this vector here is cos 2 pi on 3 because pi on 3 plus pi on 3, and then sine 2 pi on 3. It's just you can think about it as like rotating a vector in a unit circle. Yeah. Does this doesn't even look right? Okay. Okay. Evaluating it, you just get minus a half square root 3 on 2. And then if I do the other one, 0, 1, this is 0, 1 would be somewhere here, and it has an angle of pi on 2. Pi on 2 minus pi on 3 gives us this angle here, and that would be pi on 6. And so there's an angle difference in pi on 6 here, then once again, it's symmetric, so it would be like pi on 6 minus, so it will be pi on 3 minus pi on 6, which gives us pi on 6. So our vector is just cos pi on 6 sine pi on 6. And that gives us square root 3 on 2, 1 on 2. Okay, Any questions with this? It's just geometry. Okay. Yeah. Yeah, once again, just geometry. Okay. As you can see here, this is just the matrix definition of a linear map. So Q of x equals to ax. Take note that the bases must be ordered. Any linear map can be put into form Q of x equals to ax. Yeah, I think this definition once again is too problematic. Any questions with this definition? Yeah, okay. Can you guys have a go at, actually no, this is not a question. Okay, if you look at like what this is just like a linear combination of every single component. And so it's linear, so therefore it's a linear map. Yeah. Okay. This is part B of the previous question, but I don't think you need the previous question to do this question. Yeah, could you guys have a go at this question? Yeah, but we're broke, so we don't have two screens this time. Wait, hold on. Actually, no. How do I just take a screenshot? Okay, it's already too late. Okay. Oh yeah, this is part A. Note that 1, 0 and 0, 1, those are just like E1 and E2. Okay, so for this question, you're just finding the matrix A, which is just E1 and then E2. So now A is just equal to, from above, minus a half square root 3 on 2, and then square root 3 on 2, and then a half. So like this one's E1. E1 and this one's E2. Okay. The images. Yeah, so I think I should say like, yeah. Okay. And then, yeah. Okay, and then, okay, this stuff. Okay, this doesn't have space for me to write, so I'll just go through this answer. But if you want to find T4 or 5, we just use the property of the fact that it is a linear map. So we can split it up like this. And then you get your left hand side, your right hand side. That's just the definition of a linear map. Yeah. And then you just sub in your values because you know what T10 and T01 is. Any questions with this question? Okay. All right. Can you guys have a go at this question? Okay, I'm gonna go through this question now. So first of all, for part A, what we can do is we can suppose that lambda 1 plus all the way to lambda n. We suppose that this is equal to our zero vector here in V. And if we apply the linear transformation to both sides, we have this equal to T of V. By definition of a linear transformation, which is the same as a linear map, we can change it to this. And here, once again, it's just like the image, so we have 0, W. Okay. We know that from the question here, if all the TV1, TV2, TVN are linearly independent, then we just want to prove that, right? So therefore, we can assume, okay, I should write suppose here. Suppose the first statement is true. Okay, so we know that these are given to us as linearly independent, which means that, once again, all of everything here is linearly independent. And then this does equal to a zero vector, which means that lambda 1 equal to lambda 2 equal to all the way to lambda n is equal to 0. Because, once again, all of these images are linearly independent. So this is just by definition linear independence. Yeah. And because all of coefficients are 0, so therefore we can say V1, Vn are linearly independent because it's an if and only if state. So we essentially go back to our first line. Okay, and then for part B, we want to prove the converse. So if we consider, so we're gonna just consider like a counterexample. If we have t goes from r squared to r squared, and then maybe we have the map t x1, x2 gives us x1 minus x2, 0. And then we have our vectors v1 equal to 1, 0, and then v2 equals to 0, minus 1. You take a look and you realize that t1 is equal to 1, 0, and then t of v2 is also equal to 1, 0. So you have two vectors that give you the same vector. So their images are equal. If their images are equal, this means that they are linearly dependent. If they're linearly dependent, that contradicts our question, so therefore it's false. Okay, any questions? Okay, moving on. Yeah. Once again, these are solutions. Oh, and like normal, these slides will be posted online. Yeah. Okay, moving on, kernel and nullity. So a kernel is just a set of vectors that when you apply a linear transformation, it all points to the zero vector. Think about it as the roots of a linear transformation. Roots because they solve to get 0. And yeah, that's a kernel. And then nullity, I mean, you can take a look here. It's just a whole bunch of definitions. Nullity is the dimension of the kernel of T, and it's the same thing if it's a matrix. Yeah. All right. I've got this question. So here, essentially, we're just saying that like maybe a vector x equals to this chunk here. You can replace T3 with like it's just a scalar, and then you can replace T5 with another scalar, and then you're essentially you just want to find the basis, which means two linearly independent vectors that span this vector. I think this question is like a little bit trivial, but it might be a little bit like hard because this question is just okay. Maybe this question is just not that good. Okay, I'll just quickly do it. But essentially, if we can just take out T3, and then we should get -5, 4, 1, 0, 0, and plus T5, which is -12, 6, 0, 2, 1. And so, as you can see, we took out the T3, took out the T5. These two are just coefficients. We can just say that the kernel of A is equal to the span of these two vectors, -5, 4, 1, 0, 0, and then -12, 6, 0, 2, 1. Okay, yeah, that's pretty much it. I think, wait, I don't think this question is too good. Okay, moving on, image and rank. I mean, like, all of these were, yeah, these are just definitions. Okay, the image is just kind of like your y value, right? After you apply something to your x value, it's just your result. So yeah, hence you can see it's a range of a linear transformation. And then our rank dimension of the image. Okay, yeah. This is the context of nullity and rank. I'm pretty sure this was in our lab test. Yeah. Practice question in the lab test. Rank nullity theorem. Also use that in the lab test. Yeah, just the theorem. Okay. Any questions with like rank nullity images? All of these? No? Okay. Okay, I think have a go at this question. I think this is the last question. I'll give you guys 3 minutes. Okay, I'm gonna go through this question. So first of all, I'm gonna say that a vector B belongs to the image of D if and only if the system dx equals to B. Right, so we then consider the matrix here. So 0, 2, 3, 5, minus 2, minus 3, 15, minus 4, minus 6, B1, B2, B3. Okay. Once again, same thing, we row reduce it, and then what we realize is that if you look at this row and this row, well, if you times 3 on 2 to the second row, you get the third row exactly, right? So essentially, I don't even have to completely row reduce it. All we have to know is that B3 equals to 3 on 2 B2. Wait. Oh, sorry. I need to write is consistent. Right, and if B3 equals to 3 on 2 B2, then we do have a system that is consistent. Okay. This is our main condition here. So all we have to write is image of D equals to B1, B2, B3 cubed 3B2 equals to 2B3. Okay. Yeah. For part B, we want to find a basis for the image of D. So we once again have to row reduce. If we do row reduce, okay, you should get 2 minus 2 minus 4, 0, 5, 15, 0, 0, 0. You can row reduce it fully or like to this point, it doesn't really matter. What you know is that there's 2 leading columns. So the first 2, right? And then so those are our 2 linearly independent vectors. And so we just write that B is equal to 0, 2, 3, and then 5 minus 2 minus 3. Okay. For part C, what do we want to find? We want to find rank of D and nullity of D. So we can straight up find rank because there are 2 vectors in the basis of the image of D. So our rank of D is equal to 2. And by the rank nullity theorem, we have 3 columns, and so therefore our nullity of D is just equal to 3 minus 2, the rank, right, which is equal to 1. Okay, and then for part D, we want to find a basis of R cubed that contains B. Okay, so basis of R cubed, which means that we need 3 linearly independent vectors. Right now we have 2. To find the third one, a very easy way that we can do it is just use the cross product, because we know that the cross product will be linearly independent to those 2 vectors. Like definitely, right? So if we just take the cross product, 0, 2, 3, cross minus 2, minus 3, you should get minus 3, 0, 15, minus 10. Yeah, so this here is our third vector, so therefore we can just say that we have 0, 2, 3, 5, minus 2, minus 3, and then 0, 15, minus 10 as our 3 vectors. Okay, yeah. Okay, yeah, that's pretty much it for linear transformations. Any questions with this question? Okay. I'll let Xiang for that.
Okay, so you press this. Okay.
And then you select this.
Okay. Is there if okay. Hello everybody. My name is Chiang Ning. I'll be taking over from Justin Gu's excellent presentation so far. And I'll be going through eigenvalues and eigenvectors and the probability section. Right. So if you guys recall, what an eigenvector is, basically it's a we can talk about eigenvectors of both linear transformations and matrices, but since we have that theorem that like every linear transformation has a corresponding matrix, basically we usually only talk about eigenvalues and eigenvectors in terms of matrices because they're easier to work with. So basically eigenvectors are vectors for a matrix such that if you matrix multiply that matrix with that vector, you'll just get back a scalar multiple of itself. So like you can view matrices as having some spatial transformation of some Euclidean space, like for example in 2D, where eigenvectors are the vectors that just get sent to a scaled up or scaled down or like potentially flipped version of themselves in that space, right? And like the exact definition is there, the A, B, and N by N matrix, the scalar, and if we have a scalar in our field and V being a non-zero vector in f of n, if this vector and scalar satisfy the equation, matrix A times vector equals lambda vector, then lambda is what we call an eigenvalue of A. We can have multiple of those, and V is the corresponding eigenvector. So I mean that's all well and good, but how do we find eigenvalues of a matrix, eigenvalues and eigenvectors? Well, we know that lambda is an eigenvalue of A if and only if the determinant of A minus lambda I equals 0. If you want to know where that comes from, basically we know that AV minus lambda V equals 0 from before if V is an eigenvector, and we can actually factor out A minus lambda I from V since we have that matrix multiplication distributes over addition, and we know that this only has non-zero solutions if and only if the determinant of this matrix is 0, right? And V is an eigenvector of A that corresponds to lambda if and only if it fulfills this equation right here, which I've shown you. And it has to be non-zero, otherwise every eigenvalue would have a trivial 0 eigenvector, and that's not particularly interesting to talk about. So we enforce that eigenvectors shouldn't be the 0 vector. And this determinant right here is also known as the characteristic polynomial of degree n in lambda, right? If it turns out that if you, like for any degree, like for any square matrix, if you calculate this determinant, you will get a polynomial in terms of lambda, and its degree will be n. And you can prove that just by writing out the whole thing and then calculating its determinant, but like that's a lot of work and not particularly interesting. But you can prove that like just by hand, by expanding out an n by n matrix. And it turns out that if we consider every single eigenvector corresponding to a particular eigenvalue, that itself forms a vector space, right? So we call that the eigenspace of A corresponding to the eigenvalue lambda. Which is the set of all vectors such that A times the vector is lambda times the vector. And it's going to be a subspace of F and N. And you can prove that it's actually a vector space just by using the subspace theorem, right? Just like obviously contains the 0 vector. It's closed under scalar multiplication, obviously, and it's closed under scalar addition. Okay, so theorem 1 talks about the existence of eigenvalues, right? So an n by n matrix has exactly n eigenvalues if you count the real and complex eigenvalues, right? And if you have a repeated root of your characteristic polynomial, you count that twice, or however many times you have that root repeated, right? So if your characteristic polynomial ends up being like lambda squared minus 1, then we'll count 1 as a root 2 times, right? And that's just because of like the fundamental theorem of algebra, right? The characteristic polynomial has degree n, so it will have n eigenvalues. Another theorem you guys should know is that if a matrix has distinct eigenvalues for every corresponding eigenvectors v1, v2, all the way up to vk, then the eigenvectors are linearly independent, and you can let's see this. You can prove that by I think left multiplying it by a and then showing that, and then everything gets scaled up by a different amount. So like if these sum to 0, if you've, okay, I'm not going to prove it, but like that's essentially the idea. Like you set up like lambda 1 v1 plus lambda 2 v2 plus dot 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 plus lambda k vk equals 0, and then you left multiply it by a, and then these get scaled out by a different amount, and like you can conclude from that all the lambdas have to be 0, so they're linearly independent. Okay, that's all well and useful, but like, okay, that's all nice and all, but how are eigenvectors and eigenvalues useful? Well, their main use comes with diagonalizing matrices, right? So if you have if A is an n by n matrix with n linearly independent eigenvectors, right, then there exists an invertible matrix M and a diagonal matrix, which means the only non-zero entries are in its top left to bottom right diagonal, such that A can be expressed as M times D times M inverse, right? Where the diagonal entries of D are the eigenvalues of A, and the columns of N are the corresponding eigenvectors of A. And the reason that's true is basically because if you right multiply both sides with M, you get like AM equals MD. And remember, this is sort of saying like for each vector, like each vector in each column vector of M gets scaled up by its eigenvalue, right? Because we said M was made of the eigenvectors, and the same thing happens with the right hand side. So these two matrices on the left and right are equal. And we know that A is diagonalizable if and only if it has n linearly independent eigenvectors, right? One direction is easy, like if it has n linearly independent eigenvectors, well, we can just make M directly. If it has less than n linearly independent eigenvectors, like we can't find them, then it turns out that M is not invertible, so we can't make that form, right? Yeah, for M to be invertible, the eigenvectors must be linearly independent. Right, so let's go through an example. I'll give you guys like a few minutes to think about it. This was in the past papers provided on the side, by the way. So you might see something like this in your finals as well. So Okay, so can anyone tell me what the characteristic polynomial of A is? Well, okay, so to get the characteristic polynomial, right? Well, we want to find the eigenvalues of this first, right? Or potential eigenvalues, right? So we should look at the characteristic polynomial, which is given by determinant of A minus lambda I, which is going to be the determinant of 22 minus lambda, x, negative 43, 31 minus lambda, which if you expand it out is going to be something like lambda squared minus 53 lambda plus 682, sorry. And then plus, well, minus negative 43x, which is plus 43x. Right. So let me ask you this. If we allow like complex eigenvalues, what happens if this polynomial here has two distinct eigenvalues, two distinct solutions? Right. If this polynomial, if this quadratic has two distinct solutions, right, then we'll have two linearly independent, we can definitely find two linearly independent eigenvectors, right? If this has two distinct eigenvalue solutions. But if we have two distinct eigenvectors, two linearly independent eigenvectors, right, then we can construct a matrix, right? We can just say let M be the two linearly independent eigenvectors we found, like let the columns of M be that, and then we can diagonalize it, right? Right. If I scroll up, right, if our matrix A had two distinct eigenvalues, then we could find V1 and V2 such that they're linearly independent. And if we can find that, then we can just find M directly, right? So for A to not be diagonalizable, this quadratic here can't have two distinct solutions. Otherwise, we could diagonalize it. So that means its discriminant has to be equal to 0, right? Okay, I'm probably not gonna calculate it out for you. Let's see, the discriminant, oh sorry, I don't need the square root. So the discriminant is 53 squared minus 4 times 682 minus 4 times 43x, right? And we know that this has to be equal, this has to be equal to 0 so that it has one distinct solution. I think that tells you that like something like 172x is 81, so x has to be 81 on 172. Are there any questions for that? Wait, I didn't even use the working out paper. Sorry, let me draw it down here. So discriminant equals 0, 53 squared minus 4 times 682 minus 4 times 43x equals 0. 172x equals 81. X equals 81. Any questions for this? All right, let's move on then. Yes. Okay, so why would we want to diagonalize a matrix? Well, oftentimes questions will ask, well, like there are many real world applications for like modeling systems with matrix multiplication, right? Remember like Markov chains in the lectures? You can like situations where the next state only depends on the current state. Often those are very easily modeled by repeated matrix multiplication. So we could want to kind of want to see, is there a quick way to multiply big matrices together? Because like if I had to like cube a 100 by 100 matrix by hand, that would be awful, right? So diagonalization makes it really easy to power matrices, right? Because like if I have like a squared or something, I'd get m times d times m inverse times itself, right? But then these m's here, right, m inverse and m here, they cancel to be the identity, right? So like this cancels, this cancels, this cancels, and so on and so forth, right? So what I'm left with, if I multiply our matrix by itself and it's diagonal and it's diagonalizable, I'll just be left with m d to the k and m inverse, right? So diagonalization makes it really easy to multiply matrices by themselves together. because diagonal matrices are easy to power, because you just raise the individual entries to that power, right? So we can evaluate a to the power of 4 using eigenvectors where a equals 2, 2, 1, 3, right? So first of all, a equals 2, 2, 1, 3. First of all, we want to find the eigenvectors, so we'll calculate the characteristic polynomial, which is this. It's given by 2 minus lambda, 3 minus lambda, minus 2. If I expand that, I get lambda squared minus 5 lambda plus 6 minus 2 plus 4. So I get that the eigenvectors, okay, and this is 0, so I get that lambda is either 1 or 4. So we'll just look at the eigenvectors corresponding to that. So we know that, okay, let's look at the eigenvectors corresponding to 1. We know that it should fulfill this equation, right? It should be in the kernel of a minus I, but a minus I is going to be 1, 2, 1, 2, right? And I can just see directly that if I multiply this by negative 2, 1, right, I'll get the 0 vector, right? So the eigenvalue 1 has eigenvector negative 2, 1. I can do a similar thing for 4, right? If I calculate what a minus 4i is, I get negative 2, negative 1 here. So that means I see directly that just 1, 1 also is in the kernel of that. So 4 has eigenvector 1, 1 corresponding to it. That means my m can be written as negative 2, 1, 1, 1, just by taking the columns to be the eigenvectors, while my d will just be the eigenvalue. So 1, 0, 0, 4. Now, what did I want to calculate? A to the 4, right? Oh, by the way, M inverse, for 2 by 2 matrices, to calculate the inverse, you go 1 divided by its determinant. So 1 divided by negative 2 times 1 is negative 2, minus 1 is 3, so its determinant will be negative 3. Then you take the negative of this diagonal and swap these two. For bigger matrices, you will have to like augment it with the identity square matrix of the same size, and then row reduce the left back into the identity, and then whatever's on your right is your inverse. That's from 1141, if you remember that. I don't think you'll be expected to know the know how to do it for like 3 by 3 matrices, but like it's always good to keep in mind. Anyway, so we want a to the 4, so that will just be m times d to the 4 times m inverse. So if we calculate that, that's going to be negative 2, 1, 1, 1, 0, 1, 0, 0. 4 to the 4 is 256 times negative 1/3 times 1, negative 1, negative 1, negative 2. And, okay, negative 1/3, 256, 1, 256 times 1, negative 1, negative 1, negative 2, and 1/3, negative 258, 2 minus, okay, negative 510, 1, negative 255, negative 13. Something like that. Let's check the answers. Okay. I think I did something wrong somewhere, but like that was probably an algebra error somewhere. So, but like the main idea is first you find the eigenvectors, and then you construct the m. You can find what m and d are just by looking at the eigenvalues and eigenvectors, and then powering it is easy. Okay, unless you're doing numeric calculations, because apparently I can't do math anymore. But like, any questions on that? Yes? M? Oh, M, you get M just by putting in the column vectors of M, right, would just be the eigenvectors you calculate here, right? So this left column of M here is this eigenvector here.
This right column of M here is the eigenvector here, right?
Make sure it's corresponding with the
And yes, note that this has eigenvalue 1, so we put 1 here in the diagonal matrix, and the eigenvector here corresponds to the eigenvalue 4, which was why we put 4 here, right? Like if we swap the order, right, you could also choose M to be like 1, 1, negative 2, 1, and then D would be 4, 0, 0, 1, right? But there's lots of ways to do that. If I calculated M inverse from there, it would have to give me the same result. But like, it doesn't matter what order we put the eigenvectors in, just so long as they correspond to the diagonal, to correspond to the eigenvalue in the diagonal matrix.
So they can
Sorry?
they can lambda over this like
Oh, what do you mean? Oh, like this was when I was solving for the eigenvector corresponding to lambda equals 4. But you do the same thing for lambda equals 1, right? If you wanted to find this, right, you would just say, okay, let me look at this matrix, right? That's going to be 1, 2, 1, 2, right? And then you look at what's in its null space, right? And I see that 1 and negative 1. Huh? Oh, sorry. Negative 2, 1. Like if I multiply that by the matrix, then I get 0, 0, right? So this would be the eigenvector corresponding to 1. And you do that for each other eigenvalue, and then you can find an eigenvector for that, and then that's how you make your M. Okay, any other questions? No? Okay, so let's do a harder question. So a real n by n matrix A has n distinct eigenvalues and can be represented as M inverse dm, where M is an invertible matrix and D is the diagonal matrix with lambda 1, so on and so forth, as its diagonal entries. Write the characteristic polynomial P of x of A as this thing by replacing the variable x with the matrix D and A0 with A0I, where I is the n by n identity matrix. Prove that P of D equals the 0 vector. Oh, sorry, 0 matrix. Okay, so first of all, let's write out what P of D is exactly. So we just plug in D, x equals D, so we get P of D is D to the n plus an minus 1, D to the n minus 1, plus dot dot dot, plus a1 times D, plus a0i, right? Okay. We know that since D is diagonal, like if D, for example, let's say D equals like lambda 1, lambda 2, dot dot dot, lambda n, where everything else is 0, right? Right? D is an n by n matrix. If I look at what D to the n is, right? D to the n, that would just be lambda 1, oh, D to the k, sorry. Lambda 1 to the k, lambda 2 to the k, dot dot dot, lambda n to the power of k, right? Everything else is 0. So, and I know that this, okay, we want to show that this is equal to the 0 matrix, right? This up here. I want to prove that this is equal to the 0 matrix. Sorry, that looks like a vector. Just, that's a 0 matrix, not 0. But what we can do is look at the columns, right? So look at the individual entries, right? So let's look at the top left entry, right? Top left entry of D to the, P of D, right? What we'll have is D to the n is going to give top left entry lambda 1 to the n. D to the n minus 1 is going to have top left entry lambda 1 to the n minus 1. And so on and so forth, right? Plus a1 lambda 1 plus. And I, the identity matrix, will have top left entry 1, so this will be a0, right? But, okay. Remember what lambda 1 is, right? Lambda 1 is an eigenvalue of A, right? That means it's a root of the characteristic polynomial, right? So lambda 1 is an eigenvalue of A, so is a root of the characteristic polynomial of A, right? But what we know that P of X is the characteristic polynomial of A, right? So that means this whole thing here at the top is just, this is equal to P of lambda 1, right? Which is 0, just by definition, because the eigenvalues satisfy the characteristic polynomial, right? And we can repeat this for like this entry here, right? If we look at like second row, second column, we'll have the exact same situation, except like the entry in the second row, second column will be P of lambda 2, right? Which is also 0, right? And so all the entries on the main diagonal of this will all be 0, right? Just by definition of eigenvalue. And everything else that's not in the diagonal is 0 everywhere, right? All of these matrices have 0 if it's not on the main diagonal. So they'll also be 0. So we do indeed have that P of D gives the 0 matrix, right? Are we all good with that so far? Okay. Hence or otherwise prove P of A equals 0. Okay, so what do we want? We want P of A. We know that that's equal to A to the power of n. Oh, sorry, A n to the times A to the n. Wait, sorry. Oh, wait, that doesn't have a coefficient. My bad. So, plus, we want to show that this thing plus dot 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 plus A0I is equal to the 0 matrix. Want to prove this, right? Okay, so first of all, let's notice that this is very similar to what we proved before here, right? So we want to relate, so in some sense, we want to relate this to this, right? How can we get from one to the other? Well, we can notice that no matter what n is, a to the n will always be m inverse dm. Okay, they've switched the order of the inverses around, right? So, but like, we have that this is true for all natural numbers, right? What that means is that, what that means is that if we look at what m inverse times P of A times m is, we'll get m inverse A to the n times m. Oh, sorry, the wrong order. We should look at what this times P of D is, right? We'll get m inverse d to the n times m plus a n minus 1 m inverse d to the n minus 1 m plus dot 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 plus all the way up until m inverse a0 m inverse d to the 0 technically, right? Because that's the identity times f, right? Well, what do we know about the left-hand side? Well, from earlier, we've proved that P of D is the 0 matrix, right? So all of this stuff is just equal to the 0 matrix, right? Not vector, sorry. What is this? Well, we know that m inverse d to the n times m is going to be a to the n. This is going to be a to the n minus 1, and so on and so forth. And this is going to be a to the 0, or the identity, right? So all of this will just be equal to P of A, right? So P of A must therefore equal the 0 matrix. Are we all good with that? Hence or otherwise, show that, using the result in part 2, show that the matrix satisfies that. Okay, well, this is probably going to be very simple. 2, 4, 1, 1, negative 1. 2, 4, 1, negative 1. We'll just look at the characteristic polynomial of this. So determinant of this minus lambda equals 2 minus lambda, negative 1 minus lambda, minus 4 It's going to be lambda squared minus lambda minus 2 minus 6, right? So P lambda equals this. We know from part 2 that P of A equals A squared minus A minus 6 equals 0. The zero matrix, 6i. So we get that A squared equals A plus 6i as desired. Okay, so we can also solve a system of differential equations using this, right? So, for example, if we have first order ordinary differential equations with multiple variables, what we can do is say, okay, for this one right here, we can say let v equals the vector xy and define dv dt to be dx dt dy dt, right? What we have now is that dv dt is going to be some vector multiple, okay, 4 negative 2 1 1 times xy, right? To solve these, we'll do the exact same thing as before, or we'll do a similar thing to before, right? We'll find the eigenvectors of this, right? And then each of these eigenvectors will correspond to a solution to the differential equation just by multiplying by like e to the lambda t, right? If we have an eigenvector, let's say v is our eigenvector, then dv, and it has to be constant, dv dt will be lambda e to the, if we have an eigenvector, let's call it u actually, so I'm not mixing names, and we set v equals that, then dv dt would just be lambda e to the lambda t u, which is going to be lambda v, which is going to be equal to av, right? If u is a eigenvector, right? Because v will also be an eigenvector, right? So we should look at the eigenvectors of this. Let's look at the characteristic polynomial, right? 2 equals 0, lambda squared minus 5 lambda plus 6 equals 0, lambda equals 2, 3. The corresponding matrices will be 2, negative 2, 1, negative 1. So this has solution 1, 1. For 3, we have 1, negative 2, 1, negative 2. So we have solution 2, 1. So our eigenvectors will be 1, 1 with eigenvalue 2, and 3 with eigenvector 2, 1 with eigenvalue 3. That means our solutions will be of the form e to the 2t times 1, 1 and e to the 3t times 2, 1. Or like if you wanted to write it inside the thing, you could also write it like this. General solutions to the differential equation will therefore be given by scalar linear combinations of these vectors. So it will look like this. So solutions are therefore given by this, plus b t to 1. So remember, if you remember, v is x of t, y of t, and we say that this is equal to a e to the 2. Why do I keep writing 3? 2t plus 2b e to the 3t, a e to the 2t plus b e to the 3t. Right? So that gives us a general set of equations. X of t equals a e to the 2t plus 2b e to the 3t, and yt equals a e to the 2t plus b e to the 3t. Now for the second, we can also use this to solve higher order ordinary differential equations by defining new variables, right? So first of all, we will let I'll let v again be our solution vector, right? What should our vector be? Well, if we let the two variables we want to consider be y and dy dt, notice that dv dt is going to be equal to dy dt and the second derivative of y with respect to t. Now, from the differential equation, we know that the second derivative of y is going to be equal to 2 times the first derivative plus 24 times y, right? What that means is that we can express this new vector as in terms of a matrix times the vector y dy dt, just by having the matrix be 0, 1 and 24, 2, right? And so we get that the differential equation satisfies this form, right? That means we again do the same thing. We want to find the eigenvectors and eigenvalues of this. So we get the characteristic equation is this. So we get lambda squared minus 2 lambda minus 24 equals 0. Lambda minus 6 lambda plus 4 equals 0. Lambda equals 6 negative 4. Right, so let's look at what they correspond to, right? We have negative 6, 1, 24, negative 4. So that times 1, 6 should give the 0 vector. And for the other one, subtract the negative 4, we get that 1, negative 4 gives the 0 vector. So our eigenvectors will be 6 corresponding to 1 and 6 corresponding to eigenvalue 6, and 1 and negative 4 corresponding to eigenvalue negative 4. So that means our general solutions will be given by a e to the 6t times 1, 6 and plus b e to the negative 4t times 1, negative 4. And v, and v is of course y dy dt. So we were looking for y, so that tells us that y of t is going to be equal to a e to the 6t plus b e to the negative 4t. Any questions on that? Yes?
Yeah, maybe we can visit this. So when do we find this question we're solving?
Good question. I think these are just made up for the slides. Like the slides will be uploaded online afterwards. So on our Discord server, right? Somewhere. Oh, website, sorry. On the website. So you can always go back and access these slides later on if you want to go over the questions yourself. Right?
It's like for the MATH1231.
Well, yeah, MATH1231, MATH1241. This is also being live streamed, right? So you'll also see the video on our channel if you want to rewatch this from the very beginning. Yeah, those are the solutions. You can read through that. But now it's time to go through probability and statistics, right? So this is all very recent stuff, so this should be at the top of your head. But if you don't quite remember, we defined a probability on a sample space, right? So our sample space was kind of like the list of every possible event that could happen. And we define a probability on it as a function that takes elements of S to the real numbers with the properties that the probability of any event happening, or the probability of a subset of S must be inclusive between 0 and 1 inclusive, right? That's basically saying like I can't have like 120% chance of something happening. And the probability of the empty set happening, either the probability of no event happening is 0, and the probability of S, meaning at least one event happens, should be 1. And we also should have that the probability of A union B should just be the sum of the individual probabilities if A and B are disjoint. That's basically saying if A and B like can't happen at the same time, then the probability of either of them happening is just the sum of the individual probabilities. From these rules, right, we can determine that the probability of A complement is like 1 minus the probability of A, and that's just because probability of A plus probability of A complement is equal to probability of A union A probability of A union A complement, right? Because they're disjoint, which is the probability of S. For this, okay, I'm not gonna go through the full thing, but like you just get that the probability of A plus the probability of B is the probability of like A plus the probability of B minus A plus the probability of A intersect B, and then you re-add that back in, and then like you get the same thing essentially. If A is a subset of B, then the probability of A is less than or equal to the probability of B. Basically, this is like if A happens, then B also happens. So therefore, the probability of A happening must be at most the probability of B happening. You can again prove this by like saying the probability of B is like the probability of A plus probability of B minus A, since this is a subset, right? A is a subset of B, and then this is at least 0. And if S is finite, then the sum of all probabilities over the individual events should equal 1. You can also prove this just by taking the union of everything here. And in fact, you can extend this to say that if S is countably infinite, countable rather, so that includes countably infinite, you get that the sum of probabilities is also 1. Because you can take the union, just these are all disjoint, so take union, and then to get S. Okay. Sorry, does anyone want me to go over anything in more detail, or? Okay. Conditional probability. So let A and B be events in a sample space such that the probability of B is not 0. So the probability of A given B is equal to the probability of A and B happening, or divided by the probability of B. So this is like saying, we're in a universe where B happened. What's the probability that A also happened in that universe? And it's the probability of A under the assumption that B has occurred. So, there's some important facts that you need to know about this. So, this you can just derive from above right here. The probability of A and B happening is just this probability of A given B times the probability of B. If you swap around B and A, like you also get the probability of B given A times the probability of A is the probability of A and B, A intersect B. So if B1, B2, all the way up to Bn partition S, then we have the total probability rule, which says the probability of A is like the sum of these probabilities multiplied together. And you can visualize this by like saying, like, suppose that this box is our S, right? And we have A here, right? That's A. If we partition this into a bunch of stuff, right? Say B1, B2, B3. This is the probability of A intersect B1, right? Which is gonna be the probability of A given B1 times the probability of B1, right? And then to get the probability of A, you just sum over this, and so on. Sum over all the regions. And you also have Bayes' rule, which you can derive from above, right? If the probability of B given A is the probability of A given B times the probability of B divided by the probability of A. Sorry, that's a bit of a mouthful, but you can just derive it from what we have up here. Okay, so mutual independence. We say events A and B are mutually independent if the probability of A and B is equal to the probability of A times the probability of B, right? Why do we define it like that? Well, if two events are independent, then that's basically saying the probability of A given B should just be the original probability, right? If B happened, then that shouldn't affect the chance of A happening if they are independent, right? And the probability of A given B is defined to be this, right? So if we just multiply both sides by probability of B, we get P of A and intersect B is, well, whatever we have on the right hand side. And this concept can be extended to events by taking any two or more of these events, right? So if A and A, B, C are mutually independent, then we should get something like this problem. And we derive it in basically the exact same way. So let's go through an example. So a particular diagnostic test is correct, 99% correct when a person has the disease and 95% correct when a person does not have the disease. Yada, yada, yada. Let me just go through it, right? So I'll label my events D for has disease and T for test positive, right? So T positive test, B has disease. So we know that 98% do not have the disease and 2% do. When they do have the disease, 0.1% of the time they have a positive test, 0.99 the times they have a negative test. If they do have the disease, we have a 0.05 chance that, 0.95 chance that they do have a positive test and a 0.05 chance they do not have a positive test. So we want the probability of the test being positive given that the person has the disease, right? So that's the probability of the test being positive and having the disease divided by the probability of having a disease, which is going to be this, which is 0.02 times 0.95 divided by 0.02, which is 0.95. So, oh, sorry, I read that in the wrong order. Sorry. Compute the probability that the person has the disease given that the test was positive. So I actually wanted to calculate the other way around. So given a positive test, right, in the right-hand side, we want to calculate the probability of them having the disease, right? So the probability of T intersect D divided by the probability of T, right? So at the top, it's still 0.2 times 0.95. But now we want to calculate the probability that they had a positive test, right? So we are looking at these two situations. So either they did not have the disease and they do have the test. So, and the test was still positive, which has a chance of 0.98 times 0.01, or they do have the disease, 0.02 chance, and they tested positive, 0.95 chance. If you calculate that, I think it's like about like 1/3. Let me check the answers. It's about 0.288, but you would just use a calculator for that. Okay, so another question. Oh, I might skip this since we're running low on time, but like again, for like these sorts of questions, just try drawing out the probability tree and calculating the individual probabilities, and then just using what we know about conditional probability up here. So let's move on to random variables, right? So oftentimes in experiments or in events, we're not, well, we do care about the outcome, but what we care about more is like about like perhaps the number of times a specific event happened, right? So to count those, we use what we call random variables, right? So random variables are defined on sample spaces, right? And they're defined as functions that take elements from our sample space to a real number, such that we say the probability of the random variable being x is equal to the probability of this set, right? Every event where x of s equals this number. So for it's hard to describe here, but like say my event was like flipping 3 coins, right? And x was like how many heads, right? Then our sample space would be like heads, 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 tails, so on and so forth, all the way up to tails, 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 right? So then x of heads, heads, heads would be 3, x of like tails, heads, tails would be 1, and x of like tails, tails, tails would be 0. So x is kind of like a function that like looks at the event in your sample space and says, okay, this variable that we're tracking, it happens so and so times in here. And so the probability of x being equal to a particular number is just like, if s is uniform, like it's the probability of those events where x has that property happen. So sorry if that's a little confusing, but I hope the concrete example cleared that up a little bit. And well, we define things similarly for probability of x less than or equal to x, right? That's just the kind of like the number, the probability over all events where xs is less than or equal to s, and so on and so forth, right? So this maps the outcome of a random experiment to real numbers. Oh yeah, for example, the random variable x could be defined to map to heads to 1 and tails to 0 when flipping a coin, right? And we call these random variables discrete if its image is countable, i.e. like the only values it can take are like 1 or like there's a countable amount of values x could take. So for example, x could be like restricted to the natural number, or x could be restricted to like only 1, 2, and 3, or so on and so forth, right? So any questions on random variable? No. Let's talk about the cumulative distribution function, right? So we talk about distribution functions of random variables, right? Where we say, okay, what's the chance that I have this or less, right? So the cumulative distribution of function of a random variable is the function we denote by f of f subscript x. Well, that takes the reals to reals, where big F of x, f subscript x of x equals the probability of our random variable being at most x, right? And oftentimes we drop this because usually we only talk about one random variable at a time, so it's obvious what it is. And properties, if a is at most b, then f of a is at least f of b, since f has to be non-decreasing, since these probabilities have to be non-negative. If a is less than or equal to b, then the probability of a being less than x, x being strictly bigger than a and at most b, is just big F of b minus big F of a. I mean, that's quite obvious. And the limit as x approaches negative infinity of f of x should be 0, right? That's basically saying x, what's the probability that x is like less than negative infinity, which is 0. And the limit as x approaches infinity of f of x should be 1. So that's basically saying, okay, what's the probability of big X being at most infinity, i.e. what's the probability of big X of X being a real number, which is, of course, 100%. And the probability distribution of a discrete random variable is a description of the probability of all events associated with X. And we denote it with P subscript K, where P subscript K is the probability of our random variable being one of a number where this is in X's domain, codomain, right? So like, what's the probability of X having this outcome? So a collection of real numbers, pk, forms a probability distribution if and only if they're all non-negative, right? Because we should expect probabilities to be non-negative, and the sum over all of them should be 1, right? Because X should have to be at least one value. Should take at least one value. And the cumulative distribution function for a discrete random variable is given by this, where the chance of x being at most, this should be, it's like, it should technically be like x of k is at most x. Basically, it's summing over all the probabilities of all the x's that big X can be that are less than what X you've provided. So we often want to we can do more things with random variables, right? We can talk about what, like, if we're playing like a gambling game, we can talk about, is this good, or like, should I expect to win over time or should I expect to lose, by looking at the mean or expected value of a discrete random variable, right? So like if I run this event many times, like what should the average of my random variable end up being, right? So it's the weighted sum of outcome values given by the sum over all k of x of k, right? Which is like the random variable that big X is tracking times the probability of that happening. And we often denote that with a mu, because mu is m stands for mean. And we can also transform random variables, right? If like one random variable is related to another by a function, right? Like if instead of asking how many heads did I get, I ask what's the value of the number of heads squared, like I can relate the expected value of those using this formula, right? The expected value of y would just be the expected value of g of x, which is essentially just I apply this function to the individual numbers in x, right? That sounds confusing, but we'll go through an example later. And we define the variance as basically how spread out our values are, right? So like it's the expected value of the squared deviations from the mean, and the standard deviation is the square root of that. And of course, remember this formula when calculating variance, because oftentimes questions will ask, okay, what's the expected value? Now what's the variance? And like we don't really want to recalculate everything again, so like if we already know the expected value, we can get the variance by looking at the expected value of that random variable squared. And what happens when we scale and shift a random variable? Well, we can like the expected value is linear, right? Not linear in the sense of linear algebra, but like we can take the a outside and the b outside. For this, the variance, if we multiply our random variable by a, the variance gets multiplied by a squared, and the b contributes nothing. A similar thing happens with the standard deviation, but like it's the square root of variance, so it only gets scaled by the absolute value of a. And remember, variance and standard deviations have to be positive. So what do we have here? So, okay. Now to talk about distributions in general. Oftentimes there are distributions we care about more than others. One of these is the Bernoulli distribution or Bernoulli trial, where these are experiments with two possible outcomes only, usually written as p equals success and q equals 1 minus p failure. Right, so it's a p chance of succeeding, 1 minus p chance of not succeeding. And Bernoulli processes consist of sequence of identical Bernoulli trials where the events sk of a success on the kth trial are mutually independent, right? So one trial doesn't affect another. And if x is a random variable that gives the total number of successes, then the probability that x is equal to k is just given by this formula: n choose k times p to the k times q to the n minus k. And like a simple combinatorics would tell you why that's true. And we define the binomial distribution as a Bernoulli process with n many trials and probability p. And well, the binomial distribution we denote as b and p, and the probability that there are k successes is given by this formula, which is just basically repeating what we had above. And if x is a binomial distribution with n trials and p chance of success, then its expected value is n times p, and its variance is n times p times q, which is np1 minus p. For example, a particularly biased coin has probability p of h 0 equals 0.7 of getting heads each time it's flipped. It costs $5 to enter a game in which the coin is flipped 12 times. You win $3 for each head. Each flip is independent of the other flips. Yada, yada, yada. Let x be the number of heads. Let y be the amount you win. Calculate the expected value of y. Okay, so we know that y is going to be, we win $3 for each head, and we lose $5 when we enter the game, right? So y equals 3x minus 5. Expected value of y would therefore be the expected value of that, which is going to be 3 times the expected value of x minus 5, right? So x is the number of heads. So in one flip, we should expect 0.7 heads on average. So this would be equal to 2.1 minus 5, which is negative 2.9. So we should expect to lose money. Oh, the coin is flipped 12 times. Sorry. X is not that. X is a binomial distribution, right? With 12 trials, 0.7 chance of success. So the expected value of x should just be 12 times 0.7, which is 8.4. So we should actually expect to win, right? 25.2 minus 5. We should expect to win about $20 each time. The variance of y, using the formula, should be the expected value of y squared minus the expected value of y all squared, which is going to be 9 times the expected value of x. Oh wait, sorry. The variance of y is going to be the variance of 3x minus 5, which is going to be 9 times the variance of x. And the variance of x is just 12 times 0.7 times 0.3, which is something. You can look that, you can just use your calculator to calculate that. But sorry, I'm rushing through these. We don't have that much time. So the geometric distribution, right, is basically a distribution of of the random variable that counts the amount of successes in an infinite Bernoulli process, the amount of trials until there's a success. Basically, the geometric distribution describes a random variable x that counts how many trials in a Bernoulli distribution until success. And we count like the last trial as well. So the first success occurs on the kth trial if and only if the first k minus 1 trials failed. So that's why we have 1 minus p to the k minus 1. So that's the chance the first k minus 1 trials fail. P is the chance it succeeds after that. And the geometric distribution forms a probability distribution because all of these are non-negative and they sum to be 1. And okay, if x is described by the geometric distribution with p, then the expected value of x is 1 on p, and the variance of x is q on p squared, or 1 minus p on p squared. Anyway, so sign tests. Let's move on to sign tests. So sign tests are basically ways we measure how lucky an outcome was. Like, so they're basically used to decide whether a comparison between two sets of figures or a set of figures and a standard can be assumed as pure luck, or if there's evidence of a difference between these two sets or the set and standard, right? So like, if I flipped a coin and I flipped like 7 heads and I had 10 coins total, like, is it possible that should we expect the coin to be a fair coin, or is it weighted such that it flips heads more often? Like, should we assume one or the other? So basically the way we do it is like we calculate the probability of that event happening, or that event or a better event relative to it happening, and if the probability of that is less than 0.05, then we should expect that our assumption that that distribution was incorrect. sorry, let's see if there's, okay, there's no examples for that. But right now, but basically, we like if in that, for example, actually there is an example here, right? So, if we look at this, right, distribution, is there evidence that students do better at algebra than they do calculus, right? So first of all, we assume that no, there's no difference, right? There's a half chance that they do better at calculus, half chance they do better at algebra, right? And from here, we see that 12 students are doing the same or better at algebra than they are at calculus, right? So we want to look at the probability of that happening or better, right? So if we want to look at the probability of 12 or more students doing better or the same at algebra than they are doing at calculus, right? So we should also look at what's the chance 13 students are doing better, or 14 or 15. And if we just sum this up using our formula, we see that there's about a 1% chance, a 2% chance of that happening. And since 2% is less than 5%, it's unlikely that the difference was pure luck. Hence, we can claim with some confidence that the students are better at algebra than they are at calculus. Sorry. Okay, so right up until this point, we've only talked about discrete random variables, right? But we can define continuous random variables, for example, like a uniform randomly chosen random variable between real number between 0 and 1. That would be a continuous distribution, right? So a random variable is continuous if and only if its cumulative function f of x is continuous and goes from 0 to 1, right? And the variable can take possible values that cover an interval of the real line, right? So if x is a continuous random variable with cumulative function f(x), the probability density function is defined as its derivative if it's differentiable at that point, or its left derivative if it's not differentiable at that point. Its left limit, the left limit of its derivative. So, and this should be non-decreasing and go from 0 to 1. Oh yeah, okay, right here. So like this is the probability density function. It should always be positive because probability shouldn't be able to be negative. This the cumulative distribution function should just be the integral from negative infinity to that point x of the probability density function. And this is true because like this is basically almost the derivative of this. So just by the fundamental theorem of calculus, that's true, right? The sum of all probabilities should be equal to 1. And if a is less than or equal to b, the probability that our continuous random variable is between a and b is equal to like non-strict. Strict and non-strict should be equal, because remember the probability of a continuous random variable being a single value should always equal 1, and it should be the integral from a to b of the probability density function. And you can get that just by saying what's the probability that x is at most b minus the probability x is at most a. And just using definition in the integral definition here. And we define expected value and variance the same way. So the expected value of a continuous random variable is just the weighted average of everything. So like f(x) kind of defines like the probability of our expected value. Not exactly, but like it determines like the expected value, the probability of our random variable being x at some point. So we should multiply it by its value, and that should give us our expected value. And we have a similar thing here, like if y can be expressed as a function times our another random variable, then we simply write the expected value gets transformed similarly. And same thing with variance and scaling / shifting. So for example, this question from the exam, a continuous random variable x has probability density function given by that. find the value of alpha, right? So, okay, first of all, we should check that this is always positive or non-negative. So we know that alpha has to be at least 0, otherwise this would be negative at some point. We should also check that the integral from negative infinity to infinity of fx should equal 1, because it has to form a probability distribution. So the integral of that, it's 0 everywhere outside of 1 and 0. So that's this integral on the left transforms to the integral from 0 to 1 of alpha 1 minus x squared. That's equal to 1. Take the alpha out. We get x minus x cubed on 3, evaluated at 1, 0, is 1 on alpha. So we get that 2/3 minus 0 is 1 on alpha. So alpha equals 3 on 2. Evaluate the expected value of x and the variance of x. Right, so the expected value of x should be the integral from negative infinity to infinity of x times f of x. Remember that f of x is 0 outside of our region, so we can just look at what it is between 0 and 1. So we get x times alpha, which is 3 on 2, 1 minus x squared dx. Again, if we just take the integral of that using power rule, we get that this expected value should be x squared on 2 minus x cubed, x to the 4 on 4, evaluated at 1 and 0, which gives us 3/2 times 1/4, or 3 on 8. And we can calculate variance by using the formula we talked about earlier, the expected value of x squared minus the expected value of x all squared. So we want to find this. Now, remember that x squared is like g of little x, where g of x equals x squared. So this expected value here should be the integral from negative infinity to infinity of x squared times f of x, which is going to be 3 on 2 times the integral from 0 to 1 of x squared minus x to the 4 dx, which is going to be 3 on 2 times cubed on 3 minus x to the 5 on 5 on 0. 1/3 minus 1/5 is 2 on 15. So we get that the variance is 1/5. Oh, sorry, the expected value of x squared is 1/5. So we get that this is 1/5 minus 9 on 64, which is 64 minus 45, 19 on 320. Yeah, 360. All right, so moving on. Okay, let's talk about the normal distribution, right? So remember we have the standard distribution is given by is the bell curve, right? It looks something like that, and that has cumulative distribution function like c times e to the alpha negative alpha x squared, something like that. And that's called the Gaussian distribution, right? Or the standard normal distribution / bell curve. And oftentimes we can scale these and move them around, like this is to get what we call normal distributions, right? So a continuous random variable with probability density function, this from R to R, where phi of x is this expression, is what we call a normal distribution with mean mu and variance sigma squared, and we denote that as saying x. This denotes x, the continuous random variable has probability distribution given by this normal function, and the standard normal distribution is the normal distribution with mean 0 and variance 1, or standard deviation 1, right? And we can transform any continuous random variable into a normal distribution by approximate it with that we can approximate we can transform any normal distribution into the standard normal distribution by subtracting the mean from the continuous random variable and then dividing by its standard deviation. And finding the normal probability involves integrating the probability density function, but that can't be done in terms of elementary function. So usually we reduce it to the standard normal distribution by using the change of variable this, and then consulting the z-score table, right? Which will be given to you in an exam. So like, basically calculate what this is, look it up in the table of values, and then it will give you the probability. So normal distributions are usually used to approximate the binomial distribution for large values of n, and generally normal distributions are used to model experiments involving a large number of identical and independent trials with several possible outcomes, right? Because like it turns out that like if we have lots of trials, like calculating or what the probability is between like 25 and 28 is usually very annoying and difficult. But like if we have a z-score table, it's much easier because we've already got it calculated for us. So there's this thing called continuity correction, which is an adjustment that is made when a continuous distribution is used to approximate a discrete one, right? Because like in this discrete one, we see that these bars have a thickness of 1. So we have to, instead of when we transform it into a continuous one, we also have to account for that by either subtracting or adding 1/2. And the cases are given by here. Sorry if this is fast, I'm trying to get through everything. And for continuous random variables, strictly less than or and less than or equal to are the same, since continuous random variables, the probability of a continuous random variable equaling a specific value is 0. So here's some examples. So question 4, an airline knows that approximately 5% of customers who buy a plane ticket do not end up taking the flight and want to leverage that information to make more money by overbooking flights. If the airline wants the chance that a plane is completely overbooked is less than 1%, how many extra tickets can they sell for a plane with 1,000 seats? Right, so we can do this by saying like let x be the number of passengers who show up when n tickets are sold, right? And okay, we can model these passengers as being independent, right? Let's say there's not too many families or something. So then x is approximately the binomial distribution with n trials, and each person has a 95% chance of being of taking a plane, right? So we can approximate this. So x may be approximated by the normal distribution with average 0.95 n and variance 0.95 times 0.05 n. Remember, this is the variance of this distribution, and we just say that's the same thing, right? So we want the probability that x is strictly bigger than 1,000 to be less than 0.01, but this left-hand side is approximately the probability of n being bigger than 1,000. So that's equal to the probability of the standard normal distribution being bigger than 1,000 minus 0.95 n over the square root of the variance being less than 1,000. And then we know that this is equal to 1 minus the probability of z being at most whatever that is, right? And we want that to be less than 0.001. So we want the probability z is at most this value.
Excuse me. Are there going to be other sessions during this week?
I do not think so, but like
For one B, there'll be a revision day.
oh yes,
Yeah, on Tuesday.
not revision seminars, but yes, there will be a super revision day in week 11 where you can get
on
that.
Tuesday, like 10 to 1. Okay, about like nothing else? Yeah, no.
I don't think.
Okay.
but we want this to be bigger than 0.99. And if we look at the z-score table, that requires alpha to be around 2.33, right? So we want, essentially that gives you a quadratic in root n, and it turns out that n is about like 1070. Sorry, like I would go through all the working, but I don't think we have enough time.
But sorry, another question. Where can I access this recording?
On our
You just
YouTube.
search up MathSoc
Yeah.
on
There's
MathSoc.
just search up UNSW MathSoc on YouTube and the channel will come up.
Okay, and this will be uploaded.
Yes.
Okay, thank you.
Yeah, the full working you guys can look at in your own time, but it's essentially the same thing, right? And same thing with this. This is another question where you basically approximate a standard normal distribution with a you approximate a binomial distribution with a standard normal distribution and check if they're consistent, right? So the last thing we're going to go through today is the exponential distribution, right? So a continuous random variable t with a probability density function given by this is what we call an exponential distribution, and it's dependent on the parameter lambda, right? There are many different exponential distributions you could have, and the expected value of t is 1 on lambda, and the variance is given by 1 on lambda squared. Right? So, okay. The police are holding a stakeout to catch a gang of criminals. On average, they spend a total of 72 hours per stakeout. Assuming the time they spend waiting is an exponential distribution, find the probability that the criminals are caught within a day, right? So we want the probability. Okay, so let t be the time in hours. So t is an exponential distribution, which is given by the question, and the expected value of t is 1 on lambda, which is 72 hours, right? So that means lambda is 1 on 72, and we want to find the probability the criminals are caught within a day. So the probability t is less than or equal to 24 is going to be equal to the integral from from 0 to 24 of our probability density function, which is going to be lambda times e to the negative lambda t dt, which is going to be negative e to the negative lambda t evaluated at 24 and 0, which is going to be like 1 minus e to the 24 negative 24 on 72, which is 1 minus e to the 1/3 negative 1/3, which is about, let's see, 0.23. So part B, find that probability. Again, the probability t is between 72 and 100. Well, that's just given by the integral from 72 to 100 of our probability density function. Essentially, we do the exact same thing. And then 172, we get, I think, like e to the negative 72 on 72 minus e to the negative 100 on 72, and which is going to be about 0.99, 119. Anyway, I think that's it. Okay. If you have the time, please scan this feedback form and leave any feedback you have, right? Look, thank you for coming and feel free to leave. Sorry, I had to speed up at the end. There was no enough time. Again, if anything is confusing, there will be a recording on the YouTube, and these slides will be available on the website. So, yeah, there's the super revision day next week, where I think we're just going through like past papers, right? Like we're just like you come in, you work on questions, we come around and help you solve if you're stuck on something. I mean, if you have time, like do come. Yeah. I'll hopefully be able to explain things like slower and in more detail and give more personalized feedback.
The explanation is fine. I just need more questions.
More questions. Okay. I see you. I hear you. Hopefully, next time we hold a revision seminar, we can get done. Other than
Guys, quick interruption to the seminar.